So let's leverage the same example as in the previous use case for understanding the random forest implementation as well as XG boosting implementation. Now, random forest, as we already know, is an ensembling technique that falls under the bagging criteria. Here, we develop n number of models in parallel by imputing randomness at two levels. First, the training data set. Second, the number of features. Now, for implementing random forest, so what I'm going to do is, we already have the train and test data sets for the classification use case already ready. And I'm going to build, so this, if you remember, this was the cross-validation and hyperparameter tuning models which we developed. And I'm going to continue on the same point. We'll just use one of those models. So let's say we say model is equal to the new model, and then we'll continue from this point. We leverage the same data sets which we already have. And this is the same use case which is taken from the HR data set, and that is HR analytics. So you can say you need to first import the modeling technique. So you'll say from sklearn.ensemble. Here we have all the ensembling techniques. From sklearn.ensemble, we'll import random forest classifier. So there's a random forest classifier and there's a random forest regressor. Random forest classifier. Now, since this is a classification use case, let's stick to random forest classifier. Now let's import it and we'll instantiate another object. So we'll say model is equal to random forest classifier. Now, the moment I open up the braces, you'll actually see a list of different parameters that we can choose from. Now, these are kind of hyperparameters that would be required. Now, you can actually ignore all of them because there are default values associated with them. But then generally, it's a good practice to at least override a few of them to get better results. So the first thing would be, let's say, number of estimators. Number of estimators is equal to the number of models you want to create. Now, as long as you have compute power, you can just keep a very high number in this to get a good model. So the default is 10. Let's create, let's say something like 1000. So it's going to create 1000 different models and it's going to combine the results from all of these 1000 models into a single model. Criterion is Gini. We have an option to actually explore entropy also, but then we can actually keep it as Gini. Maximum depth. So maximum depth can be defined as the length of the tree. So from the root node till the leaf node, if you kind of count the levels of decision nodes, so technically the more decision nodes you have, more will be the length or the depth of the tree. The depth of the tree, as it increases, it kind of tends to create overcomplicated tools. So you can say maximum depth can be restricted as 6. This is a number which you can choose with hidden try methods, but then 6 would be a good method, good estimate. Minimum samples to split. So minimum samples to split. This is a hyperparameter which will control like if you have, let's say, a scenario where you have, so the default is 2. So it keeps on splitting if it finds a condition, even if it has 3 or 4 different samples under one node. If you just increase that, let's say we create 15. So it kind of accommodates a couple of errors, like it kind of generalizes to a better extent. Again, this is a number which you can use using hidden try method. Then there is max features. So you need to decide how many features will go into each of those models. So that is we creating auto. Auto would actually be the lower version of square root. So if you pass in 10 features in all, it will take a square root of 10, that is, let's say 3 point something. So it will take 3 or either 4. Maximum leaf nodes, we can leave this for now, and there are a couple of other ones, but for now we can just ignore it. I think these are good hyperparameters to override. So now that we have these hyperparameters set, let's go ahead and create the model. Now once the model is created, let's fit the data. So we'll say X and Y. We'll pass the column name that is left. So that's the data. We're passing the data set and the data is kind of ready. It's going to take a while because we're creating 1000 different models. So it's created 1000 different models and it's created a fitted function over here. Now what you can do is, first just let's check how does it perform on the training data set. We'll say model.score and we'll pass the same thing over here, which is X and Y, and this is the training set. This is the scene data. So we see 96% accuracy. This is a huge jump from the previous model. So if you remember, even when we were doing cross-validation using grid search, we kind of got approximately 79 to 80%. With random forest, just by overriding three simple parameters, we're kind of getting 96% accuracy. Now, but then we can't be sure whether this is a really good model because we just tested the uh, accuracy over the trained dataset. What about the test dataset? So let's look at score. Let's say we just predict first using the test dataset. So we'll say y underscore pred is equal to model dot predict, and this predict will pass x underscore test. So now we have predictions for the test dataset. This is unseen data. Now let's say we'll import an evaluation metric. So we say from sklearn dot metrics, we import overall accuracy metrics, accuracy score. There we go. And let's say accuracy score of y underscore test, which is the actual, and y underscore pred. And as you see, we have approximately 96% accuracy. So there isn't a lot of difference between the trained dataset and the test dataset. So this is a very robust model, and we can see a significant jump when we move on from a normal logistic regression model to a random forest model. So this is one of the USPs of random forest. It's very easy to develop. It's relatively it's relatively easy and it's blazingly fast. You need to override a lot of parameters. And the Python ecosystem for sklearn is pretty mature. So the kind of default values it would take is also relatively good. So had you not overridden these metrics, you would have still got a fairly uh, improved version of the results which you got from logistic regression. So that's random forest. Let's explore for the same use case an XGBoost classifier. For XG boosting, so we do have boosting techniques available under sklearn, but then XG boosting is not directly available under sklearn. You would need to install a package called XGBoost. But if you have installed Anaconda, you would actually get this by default. So let's say, let's import the package. So I'm continuing for the same use case, that is for the same classification use case. Now instead of random forest model, we'll try to develop a XGBoost model. So let's say we'll say model 2 is equal to, first we need to import that. So we'll say from XGBoost import XGB classifier. There we go. So this would be the classification model. In case you're interested in a regression model, you can actually import XGB regressor, and the syntax for that remains the same. Now we'll say model 2 is XGB classifier, and then we just open up this for parameters. Now as you see, we have a different set of parameters available for boosting technique. Now the max depth is defined as 3, so let's say max depth is 6, or in fact we can keep it at 5. Learning rate is a parameter that kind of controls how much improvement is expected when you transition from one model to another model. So if it doesn't really cross a threshold, it doesn't move that. Let's say we create a lower learning rate. So learning rate can be set to 0.01. Let's say if the outcome is not really good, we can reduce that. N estimators, it is 100, let it be at 100. Silent is 2, we're using the logistic optimizer, that's fine. Rest all of them kind of look good. We can definitely override a couple of more of them, but then let's kind of stick with these and create an XGB classifier model. So it's a model 2 not fit, and we'll pass x and y of fit. Sorry, left. I'm making the same mistake again. Now this is fairly quick because we're only creating 100 ones. Now let's see what is the score. So we'll say model 2 dot score, and we'll pass the same values, that is x and y. Let's look at the score. So we kind of get 97.6. That's one level improvement over random forest. But we can't be really sure whether this is a great model unless we look at the test data set. Now, boosting techniques by default kind of tend to overfit, but that is not the case with XG boosting. XG boosting, since regularization is implemented internally, we can kind of be assured that it might not overfit. But then let's create y2 underscore pred is equal to model2 dot predict, and we'll pass, let's say we pass the same one, that is x underscore test. So we get the predictions for the unseen data set, and we'll use the same thing, that is over accuracy score, and we'll pass y2 underscore pred, and we'll pass y. So we first pass the test score, that is y underscore test, which is the true value, and then we'll pass y2 underscore pred. Now if you look at the score, damn, that's 97.6. The model is actually pretty accurate. So you can see with just a simple implementation, we are leveraging XGBoost classifier over here. And when we look at random forest, we got around 97%, 95% accuracy. The moment you're using XGBoost, you're actually getting 97.6% accuracy. That's like kind of 2% improvement. So if you look at the journey, we've kind of improved from 78 to 95 to 95 to almost 98%. Now that's like a kind of a really good model. Now we can't definitely call it a great model because we've not looked into the recall score and precision score, but that's left for later on. But overall, you can definitely see how easy it is to implement in Python ensembling technique like random forest and XGBoosting. And you can fairly see the kind of output you would expect when you're developing a model using the ensembling technique. So we kind of got great improvement over the logistic regression model when we use a random forest model. And we got an even more improved result when we use the XGBoost technique. Now, throughout these scenarios, I have kind of restricted the experimentation with just the classification model. So we have used random forest classifier, we've used XGBoosting classifier. I've kind of omitted the regressor because at a high level, it's pretty much the same. So I would recommend you to explore the alternative techniques available for regression in your spare time. So that's everything we had to cover on ensembling techniques. So we have covered ensembling techniques. We have covered basic understanding of bagging and boosting. We looked into one techniques from each of them. So we understood what is bagging, what is boosting. So we looked into respectively random forest and XGBoosting. We looked into a simple demonstration to understand how we can leverage these techniques under the Python ecosystem from sklearn. One thing which we missed out is we talked about another technique which falls under ensembling, that is called as stacking. Now, stacking essentially isn't bagging or boosting. What happens in stacking is you create, let's say, n number of models. Let's say we simplify this to 5. Now, for all of these models, you will have an output, like you'll have the prediction. Now you'll create another model, the 6th model, which will leverage the inputs as the outputs of each of these individual models. So let's say you have 5 decision trees. 5 decision trees will give you predictions on the entire data set. Now these predictions will be the feature inputs or the independent variables for the 6th model, and the 6th model will create a model which will learn to kind of automatically tune the weights that it should give to each of these models. So that's stacking. You stack 5 models, the output of 5 models into the 6th model, and the 6th model kind of learns from the predictions of all these 5 models to predict the actual output. That's stacking. It's a relatively complicated process, but then it's kind of getting very popular these days. I'll leave it to your exploration. Please explore stacking in your free time. So that's it. We have covered module 4 in a lot of depth. It was a pretty long one. I apologize for the length. This is a relatively long module compared to the first 3 modules which we had. That covers a major portion of this course, the first 4 modules, and we have kind of finished the length and breadth of all topics that we plan to cover. Now, next module is the capstone project. So we have looked into a couple of things at a relatively high level. In the next module, which is the capstone project, now this will be a relatively short module because I'll be giving you a simple use case that I'll define the business context and help you understand what is expected, how do we approach this problem, fairly guide you through the high level process, and then leave it up to you. So that's for the next module. I thank you so much for being patient throughout this module. Looking forward to meet you in the next module. Thank you.